This is the surface of the visible sun, the photosphere, upwelling cells of hot plasma like slowly churning porridge. Typically, each granulation is about 1,000 kilometers across, so if cells occupy about 1 million square kilometers, there must be about 4 million of them across the whole surface of the sun. And incidentally, this means that each one emits about a ton of radiation per second. That's a lot of energy to drive convection. And here is a computer-enhanced 3D view of the data. Watch the movement of imaginary corks floating on the surface. They gather in valleys between the granules, showing that there are larger structures stable on a lifetime of hours. We might think of them as a domain or family of granules within some convective structure. Now, if the sun had no magnetic field, there would be nothing else to see. In fact, we see a lot more different features, such as sunspots and huge prominences, moving along magnetic arches, some reaching hundreds of thousands of kilometers into space. This arch would easily encircle the Earth. And satellite detectors have recorded fierce bursts of X radiation against the darker photosphere, and sudden flares, seen here through a narrowband filter at a wavelength corresponding to hydrogen alpha light. These are all dramatic evidence of a sun whose magnetic field is highly active. This is a sunspot seen in hydrogen alpha light. Unlike most astronomical images, it's shown as a positive, so the dark center really does mean less hydrogen light from that region. Using, inappropriately, words from eclipses, these darker regions are called the umbra and the penumbra. But what does this sunspot look like in profile? Typically, the penumbra rises some 250 kilometers above the photosphere, whilst the umbra may lie in a depression as much as 1,000 kilometers deep. The magnetic field within the umbra is thousands of times stronger than in the surrounding quiescent surface, and this inhibits sideways flow of hot plasma. And this means, in turn, that not only the umbra but also the material just above it is cooler, and cooler plasma means we can see deeper, down to the 4,000 Kelvin level. In the rarefied plasma above the sunspot, the temperature rises rapidly all the way out to the corona. And there's some small hot spots at temperatures of over 6,000 Kelvin in the umbra too, but they come and go. So much for its structure. Let's look at its dynamics. This time-lapse movie clearly shows motion of plasma. First seen in 1908 by John Evershed, the flow is in two directions away from the crest of the penumbra. The surface of the penumbra may be rippled like corrugated iron sheets, and the flow shows where the magnetic field is roughly parallel to the sun's surface. Still unexplained, this Evershed flow is thought to carry away some of the magnetic energy until the sunspot just fades away. And so sunspots are rarely seen for more than a week or two, only sometimes coming around again as the sun rotates. Since sunspots normally occur in pairs, they have magnetic field patterns similar to the ones that we can make just by sprinkling iron filings over an electromagnet. The pattern shows how the field curves away from the intense regions at the poles. And if we look above the plane, we can see that the field arches up into space in great loops between the poles. Something like this is seen on the sun, but the magnetic sun is more complicated, a constantly changing mass of twisted and stretched fields interacting explosively with the plasma. And the magnetic field that emerges at the surface is only a part of the complex pattern generated by plasma flows thousands of kilometers below the photosphere, probably at the base of the convection zone. Although individual spots come and go over a matter of days in an unpredictable way, the total numbers follow a long-term pattern called the sunspot cycle. Sunspots start at high latitudes and gradually increase both in number and intensity. And as the months pass, they appear at lower and lower latitudes on each side of the equator. So a plot of their appearances takes on this form. It's often called a butterfly diagram. Each pair of wings of the butterfly takes about 11 years. But the sun as a whole reverses its polarity every 11 years, and so do the sunspots. If we take account of this alternating polarity of the spots, we see that it actually takes 22 years to come full cycle. This is the 22-year sunspot cycle. And there are other forms of activity which start at higher latitudes, overlapping the end of the previous cycle. The period's still the same, but if we include these extra forms of activity, the butterfly now has even longer swept-back wings. If we confine ourselves to a simple plot of sunspot numbers, this data stretching back a long way. The 22-year cycle is always there, but the level of activity seems to change. Here's a long, slow minimum, for instance, another unexplained solar mystery. We have some better ideas about some of the faster changes. This is an H-alpha video movie taken at Big Bear Solar Observatory showing a flare, which is a sudden brightening across many wavelengths. Well, there are certainly rapid changes here, and they reflect changes in the magnetic field. This is a complex flare with many eruptive centers, so it's rather difficult to see what's going on. Let's look at a simpler example. Here's a nice pair of spots with the lower one fragmented and a stray one at the right. And here's how they line up with the magnetic field. We'll switch between them. Notice the opposite polarities. Now, here's the new part. Doppler measurements by astronomers at Lockheed Solar and Astrophysics Laboratory show how the hot plasma is moving. Red means redshifted, that is away from us, and blue is shifted towards us. First look to the bottom right. Do you see the filament? Here it is again. See how it seems to untwist and goes crashing down to the surface. It's moving at about 100 kilometers a second. But now look towards the upper left, between the spots. There are some more blobs of matter, not all that big, but there. Did you see the flash? That was another flare. This time we'll catch it at the peak. It may be small, but it shows clearly how the flare was triggered by the moving gas. Here are some radio images from the Very Large Array in New Mexico, and together they suggest that the activity starts at the top of the loop. Look at this diagram in your notes to see a possible mechanism for the flare. Here's a recent computer simulation of a way in which tiny ripples in the magnetic field can sweep particles along and so act as an efficient accelerator. Both electrons and protons can be accelerated by plasma waves like these to enormous energies, producing bursts of X-rays and gamma rays. Perhaps even cosmic rays originate in this way somewhere in the galaxy. In this video we've shown granules, sunspots with umbra and penumbra, filaments and flares. Now it's your turn to identify these structures in a couple of sequences from Big Bear. You'll see them as raw data, as the astronomer would, straight off the camera. Here goes.